Hello learners. Imagine drawing a house. One student sketches every brick, another just outlines the walls, and a third quickly doodles a square with a triangle on top and calls it a house. Which one is correct? All of them, depending on how much detail you want. Organic chemistry works the same way. We use different types of structural representations to show the same molecule at different levels of detail. For instance, methane is written as CH4. Ethane is CH3 single bond CH3. Ethene is H2C double bond CH2. Ethyne is HC triple bond CH. And methanol is CH3OH. Each formula is correct, but each tells a different story. These conventions are like different languages, and as an organic chemist, you must be fluent in all of them. Let's begin with complete versus condensed formulas. A complete structural formula shows every single bond explicitly. For example, in ethene, written as H2C double bond CH2, the double bond is drawn as two parallel dashes. In condensed formulas, we skip some dashes and group atoms. For example, octane can be written fully as CH3-CH2-CH2-CH2-CH2-CH2-CH2-CH3. But the condensed version is written as CH3, open bracket CH2, close bracket 6, CH3. Both tell the same story, one is verbose, the other is shorthand. Just remember, condensed formulas show connectivity, while empirical formulas show only ratios of atoms. Don't confuse the two. Now comes the shorthand doodle language of chemists, bond-line formulas, also called skeletal formulas. Here, carbons are invisible. Every junction of lines is a carbon atom. Every line end is a CH3 group unless something else is marked. Hydrogen atoms are not shown, they are assumed to complete the carbon's valency. Double bonds are drawn as double lines, triple bonds as triple lines. Only heteroatoms like oxygen, nitrogen, or chlorine are written explicitly. For example, a triangle drawn with 3 lines represents cyclopropane. A pentagon represents cyclopentane. A hexagon with a chlorine atom marked at one corner is chlorocyclohexane. These formulas save enormous time in exams. The hidden rule is, if you see a corner, it's a carbon with enough hydrogen silently filling the gaps. Flat paper is not enough to show real molecules, so we use wedge and dash conventions. A solid wedge shows a bond projecting out of the page towards you. A dashed wedge shows a bond going behind the page, away from you. A straight line shows a bond lying in the plane of the page. Take methane, written as CH4. On paper it looks flat, but in reality, it is a tetrahedron with bond angles of 109.5 degrees. By drawing one hydrogen with a wedge and another with a dash, we finally capture its three-dimensional shape. This system is essential for stereochemistry and optical isomerism. In short, wedges and dashes are your 3D glasses for molecules. Let's make molecules even more tangible with molecular models. Think of them as chemistry Lego sets. The framework model shows only the bonds as sticks, no atom sizes. The ball and stick model adds balls for atoms and sticks for bonds, sometimes even springs for double bonds like in ethene. The space-filling model goes one step further. Atoms are shown as spheres to their actual van der Waals sizes, so you see how bulky molecules occupy space. For example, the CH4 ball and stick model shows clear angels, while the space-filling model shows a compact sphere. These models help us understand connectivity, geometry, and steric hindrance when bulky groups bump into each other. Now let's solve a worked example. Expand a condensed formula CH3CH to COCH to CH3 into its complete form. Step 1. Locate the carbonyl carbon, that is C double bond O. Step 2. On the left side attach an ethyl group written as CH to CH3. Step 3. On the right side attach another CH to CH3 group. Step 4. Expand all hydrogens. The final structure is CH3 single bond CH to single bond carbon double bond oxygen single bond CH to single bond CH3. This molecule is pentan-3,1, a ketone. Notice how the same molecule can wear multiple disguises, complete, condensed, bond line, but it's always the same underlying identity. So, why should we care about all these drawing styles? Because they are the language of organic chemistry. Structural representations are used in every reaction mechanism, exam, and research paper. Bond line and wedge dash are the most common professional shortcuts. Misreading them can mean misplacing a double bond or forgetting a hydrogen. Each style has a role: complete for clarity, condensed for compactness, bond line for speed, wedge dash for stereochemistry, and models for 3D reality. Think of them as different maps of the same city. One is a street map, one is a subway map, one is Google Earth view. The better you switch between them, the faster you'll navigate organic chemistry. To wrap up, practice until flipping between formulas feels natural. That fluency is your passport to mastering the reactions ahead. Catch you in the next class with more chemistry adventures.